Here we'll look at one more way to organize our data when we're doing some of these probability problems. So here's a study that was put out by the Harvard School of Public Health. 44% of college students were classified as binge drinkers, right? Which would be 5 in a row for men, 4 in a row for women. 37% said they drank moderately, and 19% did not drink at all. So a separate study found that among binge drinkers, so around college age, 17% of those had been involved in alcohol-related accidents, while among non-binge drinkers, 9%. So all of a sudden, we know something essentially about the moderate drinkers. Out of the moderate drinkers, 9% of them have had an accident. So when you start thinking through this and writing out probability statements, right, all of a sudden you got the probability of a binge drinker. Well, that's 37%. Moderate drinkers, that's excuse me, I was writing the wrong ones there. Let me erase. So binge drinkers was 44%, moderate drinkers 37%, those that abstain 19%. If you look closely, 17% of binge drinkers, right? Knowing they're a binge drinker, so that's where you get this conditional. Given that it's a binge drinker, 17% of those binge drinkers have had an accident. So given they're a binge drinker, 17% have had an accident. So 83% of binge drinkers have not had an accident. Among those that are moderate drinkers, right? While among non-bingers, so moderate drinkers, 9% of those folks have had some type of alcohol-related accident. Now, when we were doing tables before, the trick that we kind of looked for was the word both, and that's not happening here. So what's happening now is it's a little bit too complicated for a two-way table, and that's where a tree diagram would come in handy. So here's all of our conditional probabilities and original probabilities, and the question that we have to ask ourselves first is, as we set up our tree diagram, what has to happen first? Will they be drinking first, or will they have an accident? And common sense tells us that the drinking behavior has to occur before someone can have an alcohol-related accident. So we'll separate by drinking behaviors. From there, they could either have an accident or not. And now we're going to go through and put some numbers in here. So what's the probability that a randomly selected student will be a binge drinker who has had an alcohol-related accident? So in other words, we know that they've had an accident in here. So what we do is we're going to go through and we're going to put in some probabilities. So binge drinkers, that's 0.44, 0.37, and 0.19. Now notice, among binge drinkers, 17% have had an accident. So that's going to go on this branch, which means 83% of binge drinkers have had no accident. 9% of moderate drinkers have had an accident, which means 91% have not. Now, if you think about it, those that abstain from alcohol cannot cause an alcohol-related accident, so that's 0. There's a 100% chance that if we choose someone that has abstained from drinking, they're not going to have an alcohol-related accident. So from here, once we've got that set up, go and find the probabilities at the end of each branch, and that's simply by multiplying, right? 0.44 times 0.17 is 0.075, excuse me. And so what that tells us, if you want to think about it this way, this is the probability that out of all the students on campus, we get a binge drinker and they've had an accident. So 7.5% of the student body are binge drinkers and they've had an accident. Now, another way to look at this one down here, 19% of the entire student body have abstained from drinking alcohol and have not had an accident. 0% of the student body doesn't drink and caused an alcohol-related accident. So here, what's the probability a selected student has had an accident? Let me clean this up a little bit and make it a little bit easier for us to see. What's the probability we have an accident? So look closely at the chart that we've got set up and just go, where do you see accident? So here's an accident, here's an accident, here's an accident. And what we do is just add those up. So you could be a binge drinker and have an accident. That's the 0.75. You could be a moderate drinker and have an accident. That's the 0.033. I guess technically you could be abstaining and have an accident, but that's 0. So we'll just add those up. It could be one or the other. Binge, given that they've had an accident. So what basically is saying, out of all the accidents that have occurred, what's the probability we have a binge drinker? So the first thing to do is rewrite that, right? That would be binge and accident over accident. So look at your chart. Where's the probability of a binge and an accident occurring? And the probability of binge and accident would be this 0.075. And Out of all the accidents, there was a 0.108% chance of an accident. So another way to look at this is about 70% of all of alcohol-related accidents were caused by binge drinkers. Here's another example. In July 2005, this medical journal published a report. Large study suggested that among people with HIV, this test they were doing was accurate 99.7% of the time. They would give a correct positive. People without HIV, 98.5% of those tests were correctly negative. So we do have a situation where we might end up with a false positive or a false negative. So, a clinic serving an at-risk population offers this test, and they think that 15% of the patients in that area have HIV. So, an interesting thing here, what's the probability a patient tested negative is truly free of HIV? So, before we keep moving forward, let's think about what that is. We know what about this person? Do we know that they test negative or that they're free of HIV? And a quick read of the question again, what's the probability a patient that has tested negative? So we know they've tested negative. So given that they've tested negative, what's the probability that they don't have HIV? So I'm just going to use that, right? So what we do have, right, are these probabilities. So 99.7% of the tests are correctly positive. In other words, given that they have HIV, that they get a positive test, 99.7. Here, 98.5%. Given that they don't have it, right? Given that they don't have HIV, that they get a negative test, which would be here in symbols, 0.985. 15% of people have it, which means 85% of people don't have it. Now, what has to happen first in this situation? Would you have to test or have the disease before you tested positive or negative? Common sense here. You either have to have the test or have the, disease or not have it before moving forward. So it's either someone has HIV or does not. And then from there, they can either test positive or negative. So I'm using not P as negative. So what's the probability a patient testing negative is truly free of HIV? That's what we wrote before, right? Given that they are negative, that they don't have HIV. So we need to go through, we need to fill in all the numbers here. So 15% of the people have it, 85% of the people don't. Given that they have it, there's a 99.7% chance they get a positive test, which would be 0.003 here. If they don't have it, they get a negative test 98.5% of the time, which means that 0.015 or 1.5% of the time they don't. Take a moment and fill in the end of the chart, 0.1495. And this would be 0.0005. Okay. We got 0.85 times 0.985, and that'd be 0.8373, 0.85 times 0.015, 0.0128. Okay, so now it's a matter of plugging and chugging. So the probability of not positive and doesn't have HIV. So here would be this group of people right here, and that would be 0.8373. All right, there's that number. And then we need what percentage of people are not positive. Where did you get the negative tests? And the negative tests occurred right here. Here's a negative test, and here's a negative test. There's two ways to test negative. Either you have it and test negative, which is the 0.0005, or you don't have it and test negative, which is the 0.8373. Now it's just a matter of plug and chug. We would realize it's 0.994. So 99.4% of those that test negative are truly free of HIV.